All right, and hello and welcome back to Algorithms Live. So I've been away for some time, but finally coming back. So this is going to be the last episode of the 2017. But I'll be back for the new year. As soon as I get back to California, I'm going to start running episodes regularly again. So this week, our special guest is Lewin Gan. He agreed to come back and talk about this problem that he wrote for several North American ICPC contests. We also like other announcements going on in competitive programming world. Right now, the USICO December contest is running right now. You can pretty much take that anytime this weekend. Just find, I think, 4-hour block. I think that's how long it runs. And you can just take that contest, try to solve the problems. I hope you all find those interesting. And other announcements is Dion Nicholas, which was our first guest on Algorithms Live in episode 1, is a World Finals judge this year for ICPC. So congrats to him for getting a problem accepted and being a World Finals judge. That's really exciting news. And so we're looking forward to seeing his problem and seeing what World Finals set looks like this year. But yeah, let's start the episode. So Lewin, thanks for coming back on.
Oh yeah, thanks for having me again.
Yep. Yeah, I'm hoping that you can come on much more often. I think that'll be really good.
Yeah.
Yeah. So for future episodes, I think there are a lot of like techniques we can do. Co-run an episode and talk about. So it'll be a lot of fun.
Yeah, definitely.
Yeah. So let's say. Let's just introduce this problem that you wrote. So it's this problem called Rainbow Roads. And you can just introduce what the problem is asking, and then I'll draw pictures.
Okay, yeah, sure. So in this problem, you're given a tree, and each node or each edge in this tree has some color. So the colors are like labeled from like 1 through n or something. So we'll call a path in this tree rainbow if there are if every 2 adjacent edges in this path are different colors. And
so this is an example of a rainbow path right here, right? Going from this node to this node.
Right. Yeah. So this is not like saying every edge has a different color. So it's possible that a path has 2 edges that are the same color. So like if the last edge was like color 1 also again, this path is still rainbow.
Oh yeah, this is allowed. So this is a good rainbow path.
Yeah,
because it
right.
has to
so as long as
across it. Yeah.
Yeah, as long as every adjacent pair of edges is different colors, then it's like a rainbow path.
But so this path right here is not rainbow.
Yes, right? That path is not rainbow because that's 2 adjacent ones.
Okay.
Yeah. Okay, so the problem is I want to know which nodes. So if I take some node and I look at all the paths that start at that node, I can see if like all the paths are rainbow. So if that condition is true, then I'll call that node like a good node. What to do is I want to say what are all the good nodes in this tree.
Okay, so let's take a look at some of these nodes and like figure out which ones are good and which ones are bad. So I'll put labels on the nodes.
Yeah.
So this one is not a good node because this path is not rainbow, since all of them have to be rainbow, correct?
Right. Yeah, that's right.
And so similarly, this one is also not rainbow. But if you look at this one, all paths leading out of this node, I'll call it node 5, are rainbow. Yeah. You can just see
so node 5 is good.
That one's also good. And then I believe these 2 are also good as well.
3 and 4 are also good nodes. Yeah.
Okay, cool. So I guess before we dive into the solution, I wanted to ask like how you came up with this idea and what your thinking and writing process was for coming up with this idea.
Oh, yeah. I mean, I guess I've had a lot of like rainbow road problems this year. So I wrote one for NAIPC like earlier in the year with like something about like clicks. I also wrote like a rainbow path problem in like I think some Yandex algorithm contest. Yeah, I can share you the links after and you can post them. But I mean, I think they're not too related, but I liked the theme of like having colors on edges and seeing like what types of properties you can get from that. Um, yeah, so basically that's kind of how I like stumbled upon this problem. And I realized it was solved, so like that's why I proposed it. And yeah, that's kind of how it happened.
Yeah, so you didn't have like a particular solution in mind or like another type of problem you were basing it on. You were just thinking about graphs and thinking about coloring edges on graphs and seeing what properties the trees
Yeah,
would.
right. Yeah. Yeah, I
Cool.
just kind of see what came out of it. And yeah, so this problem didn't seem like too bad to do. So yeah.
Yeah. Did you think of any different kinds of variants on this problem too? Is like when you were creating it, or did you like was this the first version that you came up with and you just happened to find a solution to it?
Yeah, I mean, it's always hard to say because I don't write everything down, so it's kind of hard to remember. But I mean, like like some standard things to do is like, oh, what is like the minimum number of changes you need to make something happen, right? So I think the very first version I thought was like, what if I wanted all paths in this tree to be rainbow? And it was just like, well, actually, that's not too hard. You just don't want any two adjacent edges to be the same color. So you can solve it with some sort of like greedy or like DFS on it, right?
Mm-hmm.
So I wanted some property that was not as obvious, I guess. So like, yeah, I mean, like if you root the tree, basically, I want like all the downward paths to be rainbow. And if you try rooting it at different things, then it might not be the same at each node. So that's kind of how I like came on to this variant.
Okay, cool.
Yeah.
So let's start talking about going towards the solution and like analyzing the properties of the solution. So I think one of the things that makes this problem interesting to talk about is, and particularly if you read Lewin's rainbow click problem, it's kind of got the same property. You have to look at the problem initially and look for properties on the graph that you're given and take advantage of those properties. So let's talk about what properties this problem has for solving the problem as given. So yeah, so what are some of the properties to analyze for this graph?
Yeah, so I guess we can start with like maybe like the simplest solution and kind of see where that leads. So like the simplest solution is I just like root the tree and then I just try every node as a root and then see if that property is satisfied.
Mm-hmm.
So yeah, I guess
So yeah, if we're rooting it, so let's say we root the tree here.
Yeah.
The property is not satisfied if we're walking down the tree and then at some point we get to a situation with these double edges, right?
Yeah, right. So if like the parent and child edges are the same color, then that's bad. But it's fine if a child or like if a node has multiple children that are the same color.
Right. So if you're coming down this DFS and we have siblings that are the same color, then this is perfectly fine.
Yeah, so like that example is fine. Yep.
Yeah, so this is a good search, but this is a bad search. Okay, so that gets us like a n squared solution. It's basically just validating the problem.
Yeah, right. Okay, so basically to speed it up, I think it might help to think about trying to like eliminate bad nodes or say like which nodes can't be like rainbow.
Mm-hmm.
So from our DFS tree, we kind of see like this happens if there's like two adjacent edges of the same color, and then like there's some path that eventually touches that node.
Okay, so we end up with, yeah. So basically any path that comes in, So any path that comes in this way and then, or comes in this
Or
way,
the other way, yeah.
yeah, and then leaves this way. These are bad paths. So
Yeah.
basically, yeah.
Yeah, so basically any node within those subtrees is actually bad because like
Yeah, so like if we think of this as like a rooted subtree and ignore anything coming out of this edge, just look at the subtree this way and look at the subtree this way. Yeah, basically have two subtrees. All these nodes are bad over here and all these nodes are bad over here, right?
yeah, right.
So we can just assume everything is good and then just mark these nodes as being bad.
Yeah, right. And if we go through all of these pairs and then we eliminate all the bad nodes, that's like the only place where the bad nodes could have came from. So the remaining nodes must be good, right? Yeah. So I guess this leads to another n squared approach that's a bit too slow, but it's a bit different to think about. But we can think about it as like marking these nodes and kind of saying these nodes are bad. And then like every time we encounter this pair, we just do that DFS to like mark all the nodes in that subtree.
Yeah, so you look for all pairings of nodes of colors like this, and then you're saying just do a DFS from this root, which has some subtree and some subtree over here. Like do a DFS from this root, and then mark all these as bad, mark all these as bad.
Right. Yeah.
And I guess the other thing that could happen here is you could end up having like a node that has a lot of pairings. So you have like a really complicated star graph where all of these are the same color.
Yeah. Right.
And so if all of these are the same color, like it could even be like you could come up with like an even slower solution where you try all these pairings and then you mark them all the way down the subtree as it's going.
Yeah. Right. So like, yeah, one way to speed it up is instead of going through all the pairings, we can just look through each individual edge and then check if my neighbor has one other edge that's the same color.
Yeah. So what you're saying, let's say this was a 2 as well.
Yeah.
For this subtree, for me to want to mark this whole subtree and eliminate this entire subtree, I don't really need to know all the different things it pairs with, because this pairs with like 7 things. I just have to know that this node has another color that's the same, and then I need to mark this tree as bad.
Yeah, right.
So I can do some bookkeeping there. I can just like keep for this edge coming in as I'm walking around these edges. If I happen to know one of my siblings has the same sort of color, then I can just eliminate that entire subtree at that moment, and then move on to the next subtree, because this one just needs to know that there's a sibling that has a 1, and I can do a similar thing. And then when I get to this subtree, well, I know that none of these neighbors pair with it, so I can just not bother eliminating.
Yeah, right. That's correct.
Okay, cool. So now we're back to n squared, but a slightly smarter n squared, I guess.
Yeah, so this is just a different way of looking at it, but this way feels easier to optimize, I think, to a subquadratic solution.
Yeah. Okay. Yeah. So let's talk about because you mentioned there's like a simpler subproblem here that we're trying to solve. Let's just like really focus in on that simpler subproblem and talk about how to solve it.
Yeah, so I guess there's a few different ways you can approach this. So yeah, I guess this is like maybe the first approach of how to think about this. So one way to think about it is instead of like eliminating or add nodes, but instead we can kind of think about, we keep a counter at each node, and to eliminate a node, we just kind of increment like the subtree by 1, and we want to know like which nodes have a counter of 0 at the end.
Okay, so basically, let's say we have our tree rooted somewhere.
Yeah.
It's a little bit being a little bit lazy. Maybe we know mark everything in this subtree, mark everything in this subtree, and then mark everything in this subtree. So we know that like I want all these subtrees to increment by 1, all of this subtree to increment by 1, and all of this subtree to increment by 1.
Yeah.
And so I can just place these markers here, but then do a DFS, and that change propagates down the whole tree, right?
Yeah. So the problem with this is since we rooted the tree, we actually want to consider like arbitrary subtrees in this case, right? So we want to also have like paths that, or like we want to say increment everything that's not in this subtree.
Right. So
to complement.
Yeah, let's take another look. So we might want to say increment this entire subtree right here, right?
Yeah, right.
It's a bit weird because it's basically saying cut the edge going this way and increment that whole subtree. Or even I could do the same thing here. I could say increment everything on this subtree. So you can think of it as here's the regular graph, and I'm like mentally flipping that whole subtree this way, right?
Yeah, right.
It's basically everything else, but this is what I want to increment, and it doesn't really match our structure of the tree rooted right here.
Yeah, right.
If you were to root the tree right here, then like you flip the whole subtree, these two pieces come up. Actually, yeah, so like these two pieces would come up. Like, let me just draw the rotated subtrees. It would look something like that, right?
Yeah, right.
And then this whole subtree makes sense.
Yeah. So in this case, so yeah, I guess like it's not very clear why you would want to do the values, but the reason why I did it this way is because the complement operation, you can actually think about it as saying add 1 to the whole tree and then -1 on the subtree. And that kind of does the same thing.
So, right, so let's say this is our tree right here. Like what you really want to do is you want to increment this entire thing right here, right?
Right.
But you're saying, actually, let's add another edge. So we could say increment all of this. Well, that's actually the same as increment the entire subtree and then subtract this subtree. So I could do like a +2 here and a -1 here, and that's equivalent to, let me use a new color, just a single +1 on this blue part.
Yeah, or you just want +1, I think, on the outside, because you want it to be 0 on the.
Oh, right. Yeah.
Yeah.
+1. Whoops.
Yeah.
Yeah. So a +1 here and then subtracting 1 here. So it's like an inclusion exclusion on the whole tree.
Yeah. So that's why I kept track of the numbers, because you can't really do this easily with just like true and false. Yeah.
Okay. Very cool. All right. So then we can try to map this idea back to the original problem, right?
Yeah. So basically, the original problem, we look at some edge, and then we want to say if my neighbor has, like, if the edge is A to B, and I want to see if A has a different edge that has the same color, then I want to eliminate the subtree like below B. And then I do the same check from like B to A also.
Right. So yeah, so basically you're basically, as soon as you detect that this node is having this subtree is bad, you're just doing that check, right?
Mm-hmm. Yeah.
Okay. All right. So next problem, or next thing. So we also saw some other solutions during the contest, right?
Yeah. Right. I guess the most common other solution that I saw was like doing the elimination kind of directly. So this solution, I think, is a little bit, there's a lot more like pitfalls, I guess. So like you do have to be a bit careful on how you implement it. So I guess we can kind of describe the basic approach. So the basic approach is you still do the, you do the eliminations like naively in a sense, but you don't redo things that you've already done before. That's the basic idea.
So it's basically like a brute force style eliminations then,
Yeah,
in a way,
right.
except it's just not redoing work.
Yeah.
So
and yeah, the basic intuition is if you don't redo any work, then it should just be like linear time because you don't look at things again. But you do have to be a bit careful because there can be some tricky cases.
Okay, so in a graph like this with this color scheme, like these would be fine. But if we came across this 3-3, for example, you would do a DFS starting from this node.
Yeah, and kind of eliminate those two branches or like those.
Okay.
Yeah.
Okay, so what makes this approach tricky? Can you give me a case of like doing this naively? So if I was doing a DFS starting from this node and like hit everything else, what would be a case that would cause me a lot of problem for correctness?
So I guess it depends on what your optimization, like how do you decide, have I done this thing before or not, right?
Mm-hmm.
So I guess the main thing is, so let's say one approach might be say, if I visit a node, I just won't consider it again, right?
Mm-hmm.
That's like one way to do it. So one tricky example is like, let's say we have a star graph, but like each of the branches of the star has length 2.
So, okay, so we'll do ones here, and I'll use different colors for the numbers so it's a little clearer.
Yeah.
2's here, 3's here, and then maybe 4's here.
Right.
Or were those the same? Yellow, maybe. 4's here.
Okay, so in this case, let's say we just do the eliminations like one by one from 1, 2, 3, and 4, right?
Mm-hmm.
So if we go to 1, 1, we'll say, okay, let's eliminate like the outer node and also let's eliminate everything like the center node and those 3 branches, right? So we do that and we mark all those nodes as like visited, right?
So we would mark this, 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 this. All right.
Yeah, and also like the outer one. Yeah, so that's like one DFS and.
Mm-hmm.
Okay, so now when we go to 2, 2, we like want to do the same thing. The thing is when we visit the center node, we'll say, oh, we already like eliminated that, so we don't need to consider it again.
Mm-hmm.
But the problem with that is we don't actually eliminate the node between the 1, 1s.
I see. So these nodes would still be marked as okay, but they're really not okay. And so our DFS is failing just because that middle node wasn't being marked correctly.
Yeah, correct. So if you just say, if you just mark a node, if you visit it, that's not correct because you might miss some future things that like go at it at a different direction.
Mm-hmm. Okay, so how do you get around this problem?
Yeah, so the other approach is you mark edges as visited. So you have to say like, you can mark like the directed, like the edge in a certain direction as visited.
Mm-hmm.
So for example, if we go back to this, and we start at 1, 1 again, and we want to eliminate the center node, we can mark the like those 6 edges as visited, right?
Yeah, let's go back to red so I could mark all of these edges as visited. And so are you also marking the nodes as bad as you mark them?
Yeah, so I'm marking the nodes as bad, but I'm also marking the edges as visited just to say I won't visit this edge again.
Okay. So you can visit nodes multiple times, even if they're like marked bad. But
the main thing is nodes. Yeah.
But the main thing is not going down that subtree again.
Yeah, that's right. So I guess one problem or like one potential issue with this approach is you do have to be careful not to like consider edges that you've already marked as visited. So like, for example, if you go back, if you consider 2, 2 now, you don't want to like iterate through the X edges, even if you're not going to DFS down them, right?
Oh, right.
Because you can imagine.
Yeah, you could have that star case again. You have a lot of edges here. And then every time we run into this node, we have to do almost like an order ends check.
Yeah.
Right? And so that would make our algorithm n squared as well. So that's a pitfall.
Yeah, right. Yeah, so basically we have to be careful. We basically have to skip any edges that we marked as visited. So the easiest way to do that is just to delete it from the graph.
So instead of having an adjacency list, you have a tree set, like basically an array of tree sets, and you can remove edges and log in time as they become problematic.
Yeah, right.
Okay. Cool. So that optimizes that piece. And so then with this approach, you can just do a bunch of DFSs and get the algorithm to work as well, right?
Yeah, right. So yeah, basically this approach is kind of just like the brute force, but it's a little bit smarter. But yeah.
Yeah. And so what's the runtime of this approach? Is also O of n? No, like n log n, right?
Yeah, I mean, depends on which data structure you use. So yeah, if you use a tree set, then it's n log n. I think you could use like a hash map or hash set, and that should be order n, but doesn't matter too much, I guess.
Okay.
Yeah.
Cool. And I guess another thing that might be interesting to talk about is you said there's also like a third solution idea based on some of the structural properties of where the good nodes are in the graph. So I thought that would be interesting to talk about as well.
Yeah, right. Yeah, I guess the other thing is, yeah, so the good nodes will form some connected subset. It's possible to show. I don't know if there's an easy way to argue for it.
Well, it's like if you have, let's say we have a node and it has a bunch of colors coming in. So basically anything that leaves that node will have different colors, right? So what you basically are doing is you're saying these nodes are all good, and right. But then over here, you would also say these nodes are all good. But the problem here is it has to be the intersection of all these leaving nodes, like the intersection of all the marked goods. So another way you can think of this is we basically have bad components here.
Yeah.
And the union of the bad components tells us what the bads are. But if we take the complement of all the bad components, we get all the goods that can come out of a single subtree. And for the, it's basically De Morgan's law is one way you can think about it.
Yeah.
If I take the complement of the bad component, I have all the good nodes. Well, the intersection of all those good components gives me what's actually good. So if you have a component like this, you can only have one edge leaving that is going to be good at a given time. And you can have multiple subtrees kind of like feeding into that good set. It's kind of like more the intuition here on why this thing is going to be connected. But it just gives you a way of reasoning about why this would be a connected subgroup is you take this bad component, take the complement, and the intersection of all those complements gives you the good component. So it's always going to be shrinking because it's an intersection.
Yeah, okay. That makes sense.
Yeah, and I guess you can show that a little differently. So I'm not sure how that helps you though in this problem, but one cool thing about like noticing this kind of structure is if the problem was asking something different, knowing that region is contiguous, could help you maybe doing some like counting kind of problem, or something where the contiguous region starts to benefit you in some way.
Yeah, I think like there are some variants where I try to think of something that could take advantage of it, but it seems a bit hard to do it properly. But
Yeah, I don't know. Maybe some problem will have something where I can take advantage of this. So I guess the other thing too is sometimes the properties aren't that useful. So if you notice something like this, it just gives you the wrong solution path, but that's fine too.
Yeah.
Okay. So I guess what we're going to do now is I wanted to code your first solution, and we can talk about it, like showing this like inclusion exclusion idea, and then show some of the viewers like how you go about coding something like this with this inclusion exclusion, and then also the detection on the edges. I think is also pretty interesting. So we can go do that real quick.
Okay. Yeah.
So I wrote all right. So I will want to make sure that these aren't blurry anymore. Okay, so we have this graph, and I guess we can read it in, have a sort of edge class going, and have what the colors are and things like that.
Yeah.
So I guess we have to also. So how do you go about knowing which direction to do the marking? Because we have two types of marking, right? We have this marking above the tree and marking below the tree.
Yeah, right.
So we need to figure out how that works.
Yeah, so marking above the tree can only happen for like so you first like root the tree arbitrarily, and after you root the tree, marking above only happens if I'm considering like my edge to my parent edge.
Okay. And so I can just like make a list of these are mark above nodes and these are mark below nodes.
Yeah, I guess. Yeah.
Okay.
You can do it that way. You can also compute it during the DFS. So like while you're doing the DFS, you can compute that number, like whether you should mark above or mark below.
Okay. So what do you mean while you're doing the DFS? Like the final DFS to push the changes down?
Yeah. So like I think the way I did it was I just did a single DFS, and in that DFS I would like decide whether or not to like change my delta or not.
Okay. So yeah, let's feed in the graph. So that's the difference in color. And then I can do a single DFS. And then I guess I can do the root trick and just do a DFS from 0. So we don't even have to, I guess we can call this like ink value, right? And then did you keep like the like global sum?
Yeah,
guess that would
I had a
be,
global sum.
okay. Yeah, so I'll keep a global sum at 0. I guess inc value of 0 would be the global sum as well, but maybe this will help prevent some issues with that.
Yeah.
Maybe we can think about cleaning that up after. So you do a DFS like this. And then do you even walk the parent edge as well?
What do you mean by that? So I guess the other thing you need is you also need like color count at each node. So like I counted for each node how many colors are the frequency of each color to that node,
Okay.
or at least the ones that appeared.
Okay. So then the color count
So the
can.
color, yeah.
Do you have enough time to, or do you have the ability to make that an outside array, and then, or do you have to like do the DFS as you're going and then like know when to mark things?
Or wait, sorry, what was the question?
Yeah, I could see this working two ways. Like I could have a hash map in the node, right? Because like then it'll amortize across the whole thing. Or if I have like an outside array, because in the problem it states that the colors are going to be from 1 to n.
Right. Yeah. Yeah. I guess if you keep it as the outside, that should be fine.
Okay.
Yeah. I don't.
Yeah, we can always like change it later if that's actually a problem. But
Yeah.
what you don't want to do is you don't want to like make
Like yeah.
and make this size n. That would
I think
bad.
making the new hash map might be like safer or something, but the color count is faster, I think, because you're not going through the hash map.
Okay, well, I also the other thing is I tend to not like doing those like dictionary counter hash maps in Java just because the code gets a little clunky.
Oh yeah. Yeah, they definitely get a bit
Nicer
long.
like a counter function in Python or a counter class in Python. That's good for that. I wish there was something similar in Java, but we'll do it this way. And then if we run into a roadmap or an issue, then we can fix that.
Yeah.
So what we can do is increment.
So the first step is to just increment the color counter, and this includes the parent edge. So we want to include the parent here. And we have to remember to decrement it after we leave. So
okay, yeah, and so I can maybe just do that now. And then I also don't want to like right.
Yeah, you don't want to like propagate the color counts below. Okay, so the first one is how do I know to do like the complement or like the complement like operations here? So like that basically means just -1 on my subtree. So that happens if the color of my parent appears more than once or like at least twice.
Yeah, so I guess I can just have two different cases here. I could say, am I my parent or am I not my parent, right?
Yeah.
And then if the color count, this is when I start marking things as bad, it's color is greater than 1. Now this is where I actually care about like incrementing the global.
Yeah.
So global sum plus, and then increment value of I minus, right?
Yeah.
And then
okay, yeah. So in this case, we want to increment the child, so not I itself.
Oh, so this is a case you want to increment the child and not I.
Yeah.
Because we're exploring the subtree down. So what do you do with the middle node then?
The middle node? Oh, I mean, it's not explicitly dealt with right now,
Oh,
I guess.
right,
So
yeah,
like
because you're
we're
only
basically considering this as the root, or like this is kind of what we're doing, I guess. But we're fixing everything that's like adjacent to us right now, or like that's not ourselves.
okay. Yeah, so I guess what I want to do is I want to draw out these two cases for these if statements, because maybe this line of code is confusing people and they're not seeing how we're visualizing this.
Yeah.
So we're going down this subtree. We're doing this DFS. Yeah, let's go here. So we're going down this DFS, and we've just entered this node I. And so pointing above us, we have our node P, and these are potentially the other cases. So the two cases are this is a color that matches with something down here. And so in that case, we decrement this entire subtree, but increment everything else. So that includes our parent. So our parent is now a bad node, and then everything else is now a bad node. And so that case holds pretty validly. And then in the other case, you're saying, well, we just want to increment that subtree if this number appears more than once.
Yeah, right.
Okay. Yeah.
Okay, yeah.
Cool.
Yeah, and then after we do that, I think we just do our DFS, and so we can like push the inc values down.
And then this is the one where we just make sure that
it's not the parent. Yeah.
And we just go down. So we do. So we'll go inc value e.j plus equals inc value of I, and then do our DFS down the tree.
Yeah.
Cool. And so now we just have to figure out what's bad, because
yeah. So basically, it's bad if the global sum plus the inc value is not 0.
Okay. Yeah. So right. So can that value should never go negative, right?
Yeah, it should always be positive.
Because
or like non-negative.
Incrementing subtrees.
Yeah, right. We're always increasing something by 1 at least.
So if inc value I, so we'll do. Is it global sum minus inc value?
Or no, it's plus. It should be plus. Yeah.
Yeah. Yeah, because this is incrementing everything. This is, and then we've already done the decrement. So if it's if this is greater than 0, then we know we're bad. So we want to print out good nodes, right?
Yeah.
Yeah.
Yep.
And that should be it. So let's see if we can pass samples. Oh, oops.
I think you also need to print out like the number of nodes or something somewhere. So you need to count the number of ones that are 0. Yeah.
There. There. Oh, and S, I need to.
Oh yeah. Print it out. Yeah.
There we go.
Yeah, I guess like we had that there so you wouldn't have like empty output.
Yeah, that
it is a bit annoying.
You don't want an empty output.
Yeah.
So data samples. is there a case 0? Yeah, so case 0, so it's processing the first sample, and then one of the samples was a case 0, and then this sample was this case. Okay,
Yeah.
so let's try running it on the data because it passes samples.
Okay, yeah.
Yeah.
Nice.
Passed, 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 passed. All right, so it looks like it passed. And so one of the neat things you can see about this problem is you'll notice a lot of the difficulty in this problem. This was a difficult problem for a lot of teams. And I think a few of the judges thought this would be a little bit easier on the set side. But you'll notice this code isn't very long to solve this problem. Like you could easily think of this problem as, oh, it's just a DFS with some inclusion exclusion. And like there's not a lot going on here for this calculation. But everything about this problem is in the analysis side of the problem. It's like figuring out the structure of the graph and figuring out like the properties and how you take advantage of them. And I think that's what makes this problem a little bit tougher for some teams is like all that head work before you actually start coding. So I think it's valuable to think through problems like this where you actually have to think out what the solution is.
Mm-hmm. Yeah.
Yeah. Do you have anything to add to that, Lewin?
No, not really. I think that covered a lot of it. Yeah.
Cool. So yeah, I guess that's it for us today. Let's see if there are any questions actually in the comments before we sign off. Yeah, there was a few questions. So one was this problem inspired by Mario Kart, or was that merely a coincidence?
Oh, yeah, I mean, I guess kind of, I guess. I like names that like alliterate, so I guess I was thinking of names that would be appropriate for this like type of problem, and I guess I was like thinking of Mario Kart at the same time. So
Yeah. And so it's actually a really easy way to find out what all your problems were in North America this year is like pretty much any problem with alliteration.
Oh yeah. I think some people actually wrote some problems that alliterated but weren't mine, but I think the majority of them were mine still.
Yeah. Like the avoiding airports.
Right? Oh yeah, avoiding airports.
Yeah. There's also a good problem. Cool. Let's see if there was another one. See more questions. Yeah, it doesn't.
There's like distinct distances, enlarging enthusiasm. I think that's all. Yeah, I don't have too much.
Right. Yeah. Most of my problems ended up in SER as opposed to Pacific Northwest this year, but it was definitely a lot of fun writing this year. I think both contests ended up being fairly interesting, so
yeah,
it was a good thing.
Yeah, that's good.
Yeah, cool. And so another thing before we sign off is there was one request that I set up a GitHub account with all the code that I write on an Algorithms Live episode. And I think that's a pretty good idea. I've always, the reason I haven't done it up to this point is I just don't want to create more work for running the show than I need. I want to make sure it's sustainable and I can keep running episodes every week. But I think I might try setting up a GitHub account with all the code from previous episodes, but maybe not update it every single week. Maybe update it whenever I have time. So I think that might be a good thing because I noticed a lot of people were asking about code, and I think that maybe it would be nice to have like the segment tree I wrote or some of the solutions so you can play around with it and see what's going on. All right. Well, thanks again for coming on, Lewin. And we'll see you guys all in the new year, 2018.